Now we turn to speed. We have seen how each operation works. Next we look at how fast they are, and we will find that one thing controls everything: the height of the tree. Let's collect every operation in one table. The reason for each cost is always the same: one comparison per level of the tree. Search costs big O of h, we do one comparison per level, going down until we find the match or hit an empty link. Insert also costs big O of h, it is the same walk as search, plus one small step to attach the new node. Delete in cases 1 and 2 costs big O of h, we find the victim, then it takes big O of 1 to unlink it. Delete in case 3 also costs big O of h, we find the victim, find the successor and delete it. Every part is big O of h. Min and max cost big O of h each, is one straight walk down a side. In order is the one exception. It costs big O of n, because it must visit every node once. So almost every cost is really big O of h, and the height h decides everything. When the tree is balanced, h is big O of log n, which is fast. When the tree degenerates into a skewed list-like shape, h is big O of n, which is slow. This chart shows why height matters. The bottom axis is the number of keys. The side axis is the height. The red line is a skewed tree. Its height grows as big O of n, straight up. The green dashed line is a balanced tree. Its height grows only as big O of log n, almost flat. The surprise is this: both trees hold the same 15 keys, only the insertion order is different. If we insert in sorted order 1, 2, 3 up to 15, each key becomes the new rightmost node. The height reaches 14. That is really a list, not a tree. If instead we insert the middle key first, then each half, the height is only 3. The same keys, a much shorter tree. Search, insert, and delete all cost big O of h, so the very same code runs in big O of log n or in big O of n, depending only on the insertion order. This is what sets up Chapter 11. A plain search tree makes no promise at all about its own height. Balanced trees add a self-correcting rule, so the height stays big O of log n no matter what order the keys arrive in. And see the size of the gap. Search a billion keys. A balanced tree needs about 30 comparisons, which you could almost do by hand. A tree skewed into a chain needs up to 1 billion. Same code. Height is the only difference. Let us put a number on it. For 1 billion keys, roughly how many comparisons does a balanced search need versus a fully skewed one? Pause and guess. Here is the answer. Balanced is about log base 2 of 10 to the 9th, which is roughly 30 comparisons. Skewed is up to 1 billion. The same operation, 8 orders of magnitude apart. Let's make this concrete with 7 keys. Both sides use the keys 1 through 7, and both obey the search tree rule. The only difference is the order we insert them. On the left we insert in sorted order 1, 2, 3 up to 7. Each new key is the biggest so far, so it hangs off to the right. The tree becomes a straight chain. Its height is 6, which is n-1. Search here costs big O of n. On the right we insert root first, middle out, 4, then 2 and 6, then 1, 3, 5, 7. Now the tree is balanced and bushy. Its height is only 2. Search here costs big O of log n. Same keys, same search tree rule. Only the insertion order differs, and that alone decides whether every operation runs in big O of log n or degrades to big O of n. Chapter 11 fixes this with a self-balancing rule, so the shape is no longer left to luck.